So next step, how to build a crypto system from the simple fact that a bar to the power of e times d is equal to a bar in z over nz, with e chosen as coprime with phi of n. So remember, in z over nz, actually we can write the following thing as a to the power of e times d modulo n is equal to a, if you feel more comfortable with that. So this can be used in the following way. For RSA, the function for encryption is for your message, which is a numerical value M. So it's the plain text message. Calculate the cipher message C, which is M, your message, to the power of E modulo N. And that's a simple calculation to do to cipher a message using RSA. And fortunately, in chapter 1, we learned how to calculate M to the power of E modulo N, and especially we've seen a very efficient method to do that. Now, the function for decryption is the following. So you have your ciphertext, which is C, and then we calculate C to the power of D modulo N. As C is already M to the power of E, when we replace C by this expression, what we get is M to the power of E to the power of D modulo N. And actually, writing M to the power of E to the power of D is equivalent to write M to the power of E times D modulo N. And actually, if you look just on top of the page, the properties that we've established if E and D are well chosen here. So if E is coprime with phi of n and D obtained with the Bezout's identity, what we'll get is that from this decryption step, we get the original message. So it's the same function actually which is used. It's modular exponentiation. And what changes between the encryption and this decryption step is the exponent that's used for this calculation. So here, just to show you how encryption works, how decryption works, and a little proof that if you do encryption first, then decryption, you get the original message, just as other method you've seen in chapter 2. So what's the difference between this system and other systems? For the previous systems, actually, which are symmetric systems, the key or the keys are shared and must not be known by anyone except the person who wants to exchange messages. Here, with RSA, the key for the encryption step is the couple N and E. Once you know N and E, you choose a message and you compute M to the power of E modulo N. You need no other information. The key for the decryption step is the couple N T. And what's really different from the other systems is that you can publish the value of E and keep the value of D. In symmetric systems, once you know the key for encryption, you can get the key for decryption. Here, with RSA, the things are very different, and I'll show you why in a few seconds from now. And actually, those keys are not named share keys. The first one is a public key that you can publish to anyone with no problem. And the second one is the private key. And actually, the asymmetry of RSA also relies on the fact that encryption and decryption are not so strongly linked than with symmetric systems.